One day, on your way to school, you notice a puddle. And then on your way back from school, puddle's gone. Magic? Not exactly. You see, these particles, the water particles, are constantly in motion. And some of them at some point, or all of them at some point, are going to have enough energy to overcome the attractive forces between them and evaporate. That is, convert from the liquid water into the gaseous water. That is, converting from a liquid into a gas. Now, if we had them in a closed container, let's say in a water bottle, these water particles wouldn't have anywhere to go. We call this a closed system. And in this closed water bottle, the water is both evaporating into gas, but also that gas, that water vapor, is also condensing into water. And you might notice if you kept a water bottle beside your bed or in the fridge and you didn't open it for a while, you would notice that the water level wouldn't appear to ever change. Although if we were able to look at the molecular level, we would see that those water molecules are constantly and forever going from liquid water to gaseous water and from gaseous water to liquid water in what we call an equilibrium. Up until this point in our studies of science, we've talked about chemical reactions as going from reactants to products. Now that's still true, reactions still proceed from reactants to products, and we often look at these reactions and represent these reactions as flowing from reactants to products, and we still will. But it's important to note that once those products start to form, they too can collide and start to form reactants. So we say that all processes, be them physical or chemical, are reversible. That is, we can have reactants forming products and products forming reactants. And the easiest one to sort of visualize is linked to the analogy that I gave you at the beginning, or the scenario I gave you at the beginning, with a container of water. So if we were to imagine a container of water that had an opening in it, the water vapor is being formed from the evaporation of the water as a liquid. And if this is an open container, the water vapor, the gaseous water that's going to form, is going to evaporate and move through the opening. And eventually the water is going to decrease to such an extent that it's effectively gone or been removed from the container. But if we were to cap that container, close it, so that there's no opportunity for the water vapor to escape, then we have what we call a closed system. And what's going to happen eventually is that the rate at which the water molecules are evaporating equals the rate at which the water molecules are condensing, and we have something that we refer to as a steady state. That is, that container and the water level within that container would appear to be unchanged. So we would say that in that case, we have an equilibrium between the water that's evaporating and the water that's condensing. So when we deal with equilibrium, and more specifically in chemistry, chemical equilibrium, we talk about the rate of the forward reaction equaling the rate of the reverse reaction. Now this doesn't mean that the concentrations of the reactants are equal to the products, and that's a really important thing to note. That is, that equilibrium is not achieved when the concentration of the products is equal to the concentration of the reactants. When it is achieved is when the rate of the forward reaction is equal to the rate of the reverse reaction. So the rate at which products are being formed are equal to the rate at which reactants are being consumed. And there's a couple of important conditions, because you might be saying, well, how often does this actually happen? And to be honest, in nature, it doesn't really happen all that much. So that's why we don't tend to think about chemical reactions as being reversible. Very rarely do we have the appropriate conditions for equilibrium to occur, but it is important to note that all systems will tend towards equilibrium. That is, they will respond and behave in such a way as if they were going to achieve equilibrium. But equilibrium does require that we have a closed system. And again, very rarely in nature do we have a closed system. Let's take a look at this process and how we're going to use it quantitatively. Now, quantitatively, we have something called the equilibrium constant. And the equilibrium constant is represented by a capital K. And this constant is determined by taking the concentration of the products over the concentration of the reactants at a specific temperature. So the rate constant, which is also K, and the equilibrium constant are two different things. The rate constant is a lowercase k, and the equilibrium constant is an uppercase K. The rate constant tells us how fast the reaction is proceeding, so a higher K means that we have a faster reaction. A lower K means that we have a slower reaction, obviously, then. And the equilibrium constant, this capital K, which has a lowercase, either a C to denote concentration or an EQ to denote equilibrium, this capital K tells us to what extent. So are there more products being formed, or are there more reactants being formed? So if there's a higher concentration of products at equilibrium, we're going to have a higher value of K. If there's a higher concentration of reactants at equilibrium, we're going to have a lower value of K. So let's take a look at a few scenarios then. Let's say K were to be greater than 1. If K was greater than 1, what that would mean for us is that our numerator would have to be greater in value than our denominator, which means, since it's products over reactants, the concentration of products is greater than the concentration of reactants. So we say in this scenario that products are favored, or we say the reaction lies to the right. In fact, if we get such a great Kc, or the value of Kc is greater than 1 times 10 to the 10, we say effectively that this reaction has gone to completion. Let's take a look at the other end here. We have Kc being less than 1. If Kc is being less than 1, what that means is the denominator is greater than our numerator, and so because, again, it's products over reactants, we're going to have a greater value of reactants, and so very little product is going to be formed. So we say, in this case, the reaction's favored, or that it lies to the left. And if we have a really low K value, to the order of 1 times 10 to the negative 10, or lower, we say effectively that there's no reaction, that there's so little product formed that we say effectively there is no reaction. Now, how do we actually go about using this equilibrium constant? It's one thing to be able to calculate it, but again, it's another thing to be able to use it. So let's say we have the following general equation in which A reacts with B to produce C and D, and they are at equilibrium. If we're going to establish the Kc for this equilibrium reaction, we are going to have to plug in the concentrations at equilibrium. So it's really important that if you're trying to establish Kc, the equilibrium constant, that you use the equilibrium concentrations to determine the equilibrium constant. However, if we just know the concentrations of these particular reactants and products, and we don't necessarily know if they're at equilibrium, we can't say that we're calculating the equilibrium constant. But again, how do we actually use this? Well, let's say we're given a scenario in which we don't know if we are at equilibrium. We use something then called the reaction quotient, Qc. And Qc is set up exactly the same way as Kc is. It's that we have the concentration of the products over the concentration of the reactants, and all of those products and reactants are raised to the exponent representing the coefficient from the balanced chemical equation. The important thing to note here is that Qc is not necessarily at equilibrium. It could be, but we don't know until we calculate it and compare it to the Kc. So in all these scenarios, if you're using or calculating Qc, you have to have a Kc for that reaction to compare it to. So let's again take a look quickly at comparing Kc and Qc. Well, if we take a look at these two, we notice that, again, we have products over reactants, and that if Kc equals Qc, we can say that we are at equilibrium, because the concentration of the products over the concentration of the reactants is the same at Qc. If it is at Kc, then again, we're at equilibrium. If, however, we have a scenario in which Qc is greater than Kc, what that means is that the products concentration that we have at this particular time is greater than it would be at equilibrium. So what that means is, in order for this reaction to establish equilibrium, it has to shift in the reverse direction so that the products are consumed, the product concentration goes down, the reactant concentration comes up, until such time that the Qc equals the Kc. In the opposing scenario, where we have Kc greater than Qc, what that means is that our reactant concentration is too high, our product concentration isn't high enough, so in order for this reaction, given these Qc concentrations, to achieve equilibrium, it's going to have to proceed in such a way that the forward reaction is favored, more product is going to be formed, and the reactant is going to be used up, until such time that Qc equals Kc. And then at that time, we have achieved equilibrium. So this is how we use Qc in comparison to Kc in order to establish which direction the reaction will have to shift in order to establish equilibrium.